The Katechon Hypothesis. Part 2. Read by an artificial intelligence based on the voice of Joshua Graham. Picking up where Dagoth left off. Part 2 of The Katechon Hypothesis by Anatoly Karlin. Computing costs of cosmic expansion. Let us for the time being assume that we need 10 to the power of 16 flops to simulate a human brain. This would mean that we would need 10 to the power of 26 flops to simulate the current world population of 7.7 billion, and perhaps 10 to the power of 27, or 28 flops to simulate the entire biosphere. This is still many orders of magnitude higher than global computing capacity, which has been estimated to be around 210 to the power of 20 minus 1.5 times 10 to the power of 21 as of the end of 2015. Assuming median brain simulation requirements, 10 to the power of 18 flops, and standard rates of growth in computer hardware, 25% per annum. These two lines shouldn't intersect until late in the 21st century. Under 12 current computing paradigms, this suggests a near absolute guarantee of safety from simulation shutdown to around 2100. UN projections suggest that the world population will max out at 10-11 billion people by the end of the century. A 2004 meta-analysis of 94 historical estimates of the planet's carrying capacity, which at 7.8 billion is virtually equivalent to today's population. That said, another increase in order of magnitude during the following millennium cannot be excluded if proliferating pro-fertility genes were to reverse the demographic transition and bring the world to a state of Malthusian industrialism. Carrying capacity estimates specifically based on land food as the limiting factor produced a much higher potential population of 103 billion, which also syncs with my own estimate of 100 billion as the planet's carrying capacity under current technological levels. Such a world will require almost 10 to the power of 27 to 28 flops to simulate. However, these figures will rapidly inflate when we reach a post-human stage and start to radically expand our noosphere. This expansion can be either inwards, microscopic, running more and more computations exploiting existing solar potential, outwards, macroscopic, settling nearby star systems, galaxies, supercluster, or the entire universe, or both. Before we take a look at the computational requirements needed to simulate various expansion paths, it would behoove us to first establish some basic numbers. As mentioned above, there are about 10 billion Earth-sized planets within the Goldilocks zone of sun-like planets in our galaxy. There are also approximately 100 billion stars in our galaxy. Our local supercluster contains 50,000 galaxies. There are 100 billion galaxies in the universe. The Sun generates 3.6 times 10 to the power of 26 joules, of which 174 times 10 to the power of 17 joules reach Earth. For comparison, our entire civilization produces just 1.2 times 10 to the power of 13 joules of energy per year. I don't bother accounting for wastage, since I assume that further technological development will assure that it doesn't translate into a decline of more than an order of magnitude relative to 100% hypothetical 100% efficiency. There are currently 10 billion humans on the planet, and I posit that its carrying capacity with today's technological levels is 100 billion. Estimates for the human colonization potential of Earth-like planets is a factor of the number of stars and galaxies. I do not think there is much point in trying to estimate the human carrying capacity of like a ring world, as in between an Earth-like planet and a Dyson sphere. If we are to expand to other stars and galaxies in a substantially non-biological form, e.g., as 20-watt brains in a vat, as mind emulations, or as superintelligent AI programs, then one may assume that all surface areas will be exploited to maximize the amount of energy tapped from the stars, up to and including the construction of Dyson spheres. Robin Hanson argues that sometime during this century, the noosphere will come to be dominated by silicon-based EMS, emulated minds. EMs reproduce by copying, and since copying has trivial costs, it can be expected that M society will quickly reach its carrying capacity, depressing wages to subsistence levels. Since much of the brain's bit erasures are non-logical, Hansen suggests that EMS will be much more efficient than the 20-watt human brain, and that the Earth will be able to support as many as 10 to the power of 24 slow EMs. This presupposes decades worth more progress in increasing energy efficiency in computations, flops per watt, as well as orders of magnitude worth of optimization on brain models, as in removing non-logical computations, regardless of how much effective computing power we manage to squeeze out of EMS or AI software. The ultimate bound on our demand on the architect's computing resources is determined by energy and hardware considerations, to which we shall now turn. One rather surprising consequence of the brain's computational efficiency is that a transition to a neo-Malthusian EM, or AI civilization, running on nano-based hardware, will increase the architect's load by no more than 7 orders of magnitude. Since 3 orders of magnitude and 10 orders of magnitude had already been spent on simulating all human history and the biosphere's history, respectively, remaining a Type 1 civilization on the Kardashev scale is unlikely to put the architect's supercomputer under undue strain. However, the equation changes rapidly once we start expanding beyond Earth and its measly share of the solar flux. Every major such expansion, harnessing the energy output of the Sun, Type 2, the galaxy, Type 3, and the universe, represents an increase of 10 orders of magnitude worth of computational potential. Even if expansion was limited to purely biological human colonization of Earth-like planets in the Milky Way, transforming them into 100 billion soul hive worlds, like the Imperium of Man in the Warhammer 40K universe, it will require 10 to the power of 37 flops to simulate. That's equivalent to simulating all human history every 10th of a second. Expanding to all potential Earths in the universe would require 10 to the power of 48 flops. The fragility of biological life, coupled with the vastness of interstellar distances, means that cosmic expansion is likely to be dominated by silicon-based EMS or AIs. A typical scenario might involve a von Neumann probe, landing on asteroids, orbiting a far-off star, using the material to construct a Dyson sphere, or Dyson swarm, and converting the structure into a matryoshka brain. Based on prospective nanotechnologies, simulating just one such structure would require 10 to the power of 42 flops. Converting an entire galaxy into matryoshka brains would require 10 to the power of 53 flops in computing capacity. That's the equivalent of 10 to the power of 17 human histories every single second. It is also possible that post-humanity will invent computronium that transcends currently understood limits of engineering. So much so, perhaps, that inwards expansion will long remain more cost-effective than outwards expansion. In this scenario, it's feasible that it will eventually approach a one-to-one mapping with the architect's hardware, assuming analogous laws of physics. Once we approach the architect's geographic extent, our simulation will take longer to run than the flow of time in the basement universe. The katechon hypothesis. Forget the power of technology and science, for so much has been forgotten, never to be relearned. Forget the promise of progress and understanding, for in the grim, dark future, there is only war. There is no peace amongst the stars, only an eternity of carnage and slaughter, and the laughter of thirsting gods. Warhammer 40K. If we are indeed in a simulation, there is a risk that the simulation will break down at some stage of these cosmic expansions, forcing the architect to Ctrl-Alt-Delete us from our sector of space-time. We have no obvious way to quantify at what point this will happen, since we do not know how much computing power the architect have at their disposal, their future time orientation, the priority they allocate to ancestor simulations, or even whether their universe hews to the same physical laws as ours. As I have argued, the most that we can weakly posit is that the architect is sufficiently invested in us to have run the 10 to the power of 36 or 10 to the power of 43 operations needed to simulate the evolution of our civilization and/or biosphere, which might not have been especially interesting until recently. This establishes a lower bound for the sort of computing resources the architect has at his disposal. What effect could this be expected to have on the universe's geopolitics, its cosmopolitics? Rather paradoxically, the exact value of the simulating supercomputer's R-max value, its maximum achieved performance, may not matter nearly as much as the answers to the following questions. 1. Do alien civilizations tend to believe that they are in a simulation, or at least assign a non-trivial chance to the possibility? 2. Once a spacefaring civilization spreads beyond the parent solar system, is there any chance of controlling further expansion? As I shall argue, a certain set of answers here will provide a crisp solution to the Fermi paradox. Do aliens believe in the Matrix? Obvious caveat that alien minds are alien. There are a number of good reasons why they might seriously consider the possibility that they're in a simulation. First, the capacity to imagine the world as illusion seems to have gone together with the evolution of a complex cognitive suite. It has appeared in various forms and throughout diverse cultures in world history, including primordial folk beliefs, the dream time of Aboriginal Australians, ancient philosophy, as in Neoplatonism, Zhuangzi's butterfly dream, esoteric interpretations of the major monotheistic faiths, Kabbalah Judaism, Gnostic Christianity, Sufi Islam, and heresies, as in Cathars, Bogomils. Of these, perhaps the most fascinating ancient example is Gnosticism, as it even anticipates the idea of a simulation within a mathematical structure. The existence of the demiurge, the creator of the material world, a premonition of the architect, happens within the scope of the ultimate reality, defined by monad, the one, which is both bythos, deepest, and outside time, pro-arche, which can be considered a metaphor for the abstract mathematical structures that define the metaverse. So it seems unlikely that intelligent alien beings would have difficulty with the concept. Second, metaphysics is becoming digital physics. Since the publication of Calculating Space by Konrad Zuse in 1969, the idea that computation is existence, that we live in a mathematical universe, that can be crisply described as a set of mathematical relations, or that can be modeled as a cellular automaton or computer simulation, has become increasingly popular amongst physicists and philosophers. There is the practical observation that reality appears to be discrete at the lowest levels in both space and time, Planck units. The speed of light can be interpreted as the CPU's clock speed. The universe appears to be extremely fine-tuned, in a way that is favorable to the emergence of complex life. Furthermore, a great deal of what Einstein called quantum spookiness, collapse of the wave function on observation, or future events determining the past, can be interpreted as the universe making liberal use of simplifying calculations. Just as with Schrödinger's cat, the typical RPG video game doesn't calculate the amount of gold in a treasure chest, until you observe it. It would be surprising if aliens did not come up with broadly analogous digital physics interpretations of reality. Third, there may appear more telltale signs that we are living in a simulated universe. This could be in the form of what we might call lazy programming, such as the recent and unexpected discovery that all galaxies rotate at the same speed. Another, closely related set of possible evidence would be cosmic macrostructures that hint at an architect's involvement. One possible example is a supervoid at the CMB cold spot 6 to 10 billion light-years away. It is spherical in shape, 1,000 times larger than similar voids, and is supposed to be missing 10,000 galaxies. This translates into 10 to the power of 41 flops to simulate that amount of hive worlds, and 10 to the power of 57 flops to simulate that amount of matryoshka brains. Reminder that 10 to the power of 43 operations are needed to simulate a biosphere history. Perhaps that region of space awoke several billions of years ago, spread in an expanding sphere, and had to be wiped by the architect? Moreover, perhaps the supervoid only became so big because it was the first to go into metastasis, and the architect could wait longer before shutting it down, since computationally intensive biospheres had yet to form in other parts of the universe. These are admittedly some crazy speculations. That said, it might be possible to devise more grounded tests in the future. For instance, philosopher Michael Johnson argues that apart from ancestor simulations, there could be two other good reasons to simulate a universe. 1. Instrumentally, to calculate something. 2. Intrinsically, to create a wide variety of interesting qualia. Finding that our universe is optimized for efficient computation, or that all our contingent physical variables are fine-tuned to create maximum positive valence, could potentially greatly increase our confidence in whether or not we reside in a simulation. Max Tegmark in The Mathematical Universe argues that we do not live in a simulation because of the problem of recursion. There is no apparent way to definitively establish you're not in the basement simulation. And because simulating a universe is much more computationally intensive than merely specifying the set of relations between its elements, which is all that his mathematical universe hypothesis requires. He argues that the existence of a memory stick within our universe, containing such a set of relations, would not increase the likelihood of finding ourselves in such a universe to any appreciable degree, considering that the multiverse is infinite in scope anyway. I do not really buy this logic, because even infinities obey the laws of probability. In any sufficiently large portion of space-time, defined by our universe's rules, the chances of us being in a simulation will converge to the quantity of simulated observer moments, divided by the quantity of real observer moments. Obviously, we can only speculate about those ratios. However, as Bostrom himself points out, the mere fact of us starting up simulations, especially ancestor simulations, would massively raise the chances that we are within a simulation ourselves, at least so long as we can credibly recreate the observer moments we experience. That the ultimate reality, the one that the architect inhabits, may also be purely mathematical, has no bearing on whether or not our reality is a simulation. The monad does not rule out a demiurge. The existence of operating systems does not make impossible virtual machines, nor does it even say anything about the relative ratio of total programs running between the two. Consequently, the fourth and last point is that if aliens manage to successfully run ancestor simulations, it will increase their confidence that they are themselves in a simulation. As already mentioned, they will have a variety of reasons to run such simulations. Critically, running simulations isn't likely to strain their computing budget, at least so long as it remains fixed as a percentage of their total computing activity. The catch, of course, is that this may require repeated pruning of the simulation. Finally, It needs to be emphasized that there is no hard requirement that aliens believe or know that they are in a civilization for certain game-theoretic dynamics that will soon be expounded upon to come into play. It is merely sufficient that they either 1. Assign a non-negligible probability to such a scenario, and/or 2. Assign a high probability to other civilizations thinking in these terms, and assign a greater utility value to the survival and prosperity of their own civilization than to that of other civilizations. In both of these scenarios, even purely utilitarian considerations will dictate a certain set of cosmopolitical imperatives. Can expansion be controlled? The biological drive to expand, to exploit more ecological niches, seems to be innate to our species. This is also probably true for most intelligent alien species, since intellect evolves, in significant part, to the challenges of dealing with variegated environments. There is no reason to think space is an exception, as suggested by the sheer plethora of space opera-themed films, books, and video games. This sentiment was perhaps most succinctly expressed by Konstantin Tsiolkovsky, one of the founding fathers of rocketry. A planet is the cradle of the mind, but one cannot live in a cradle forever. Once a civilization sets up the requisite economies of scale, there are substantial material benefits to cosmic expansion. Even if increasing a civilization's power and prestige is too much of an anthropic motivation, there are no end of seemingly more universal benefits, such as increasing the energy computing power at one's disposal and providing redundancy against many forms of existential risk. This is one of Elon Musk's stated reasons for wanting to set up a Mars base. However, no post-human civilization, at least in the Milky Way, seems to have made a play for galactic domination. Moreover, we can be relatively sure that nobody in our neighborhood has gone much further than Type 2 on the Kardashev scale, as in fully harnessing the energy of its parent star. Nor is it immediately obvious why alien civilizations would hold back. After all, it's not like spreading to 2, 10, or even 100 new star systems will likely turn out to be the straw that breaks the horse's back, or short-circuits the architect's supercomputer. Increasing the computational load by many orders of magnitude, such as overspreading a supercluster with EMS. As we saw in Part 2, this is potentially much riskier. Settling just a few other worlds? Probably not. And the benefits to this are vast, since it would introduce a very substantial safety margin to a civilization's long-term prospects. But all this depends upon the critical assumption that expansion to other star systems can be indefinitely controlled. The reason is that while singletons, which can range the gamut from world dictators to global adherence to a set of ethical norms, are feasible on single planets, they become much more problematic to maintain across multiple planetary systems. The average distance between stars in our part of the Milky Way is around 5 light-years, which puts a massive lower bound on the speed of communications, not to mention physical contact, under currently understood laws of physics. Eventually, one world or another will start to ignore metropolitan edicts against further expansion. This will cause a snowballing effect, since the very fact of expansion will select for more adventurous, rebellious, fecund, and expansive cultures. Furthermore, having already defied the imperial center, this expansive culture will have strong incentives to rapidly maximize its power relative to the coalition that it is now sure to provoke against itself. This, perversely, will make it even more important for it to undertake further rapid expansion. Historically, one can make the comparison between China and Europe during the Age of Exploration. In the wake of Zheng He's treasure voyages from 1405-1433, the Chinese decided to scrap their navy to focus on the nomadic threat. As a centralized empire, It was able to institute progressive restrictions on private maritime trade, eventually limiting them to tributary missions. China was the dominant power in East Asia, both culturally and commercially. In neighboring polities, kings sought investiture from and kowtowed before the one emperor, the Son of Heaven. Consequently, the Chinese sea ban, Haijin, was also adopted by its cultural vassals, such as Japan, Sakoku, and Korea. The term Hermit Kingdom predates North Korea. The Japanese policy, which lasted from 1633 to 1853, was even more draconian than China's, prescribing the death penalty for shipwrecked foreign sailors and Japanese who left the country and then returned, as well as their families and intercessors. The fundamental reason has to do with the observation that the offensive rules supreme in space. This is a function of the sheer destructiveness of hypothetical space-based weaponry, as well as the relative ease of stealth for civilizations that are so inclined. Trivially, one may launch dense pellets or objects at very high speeds, because energy imparted is a constant of mass, but the square of speed, which furthermore becomes hyperbolic at relativistic speeds. However, aiming such a shot may be quite difficult from large distances. Alternatively, mega mirrors arranged around a star can generate a beam with the intensity of a 6,750,000 blackbody, with a diameter equal to our moon's orbit, and a diffraction rate of only 50 km per 1,500 light-years. Such a beam would maintain the intensity of a star's surface, even thousands of light-years away. Even a temporary intersection with a planet such as Earth will fry its surface to a crisp. Another, admittedly harder, possibility is to fling large planets into the sun. This isn't going into overly sci-fi weapons, such as nanomachines, that can transmute a star's mass into elements that don't support fusion, as in Peter F. Hamilton's The Neutronium Alchemist, or exotic space-time hijinks to speed up delivery times beyond light speed, e.g., Alcubierre drives or wormholes. They might be purely speculative today, but who knows what tomorrow will bring. Furthermore, even controlling a human space civilization is likely to be much easier than policing EMS or AI superintelligences. Fundamentally, this is because the latter run on electronic circuits that switch 10 billion times faster than the 20 milliseconds that human brain neurons take to react. Robin Hanson projects that the typical EM will run at 1,000 times human speed, while the very fastest cost-effective EMs will run at 1,000,000 times human speed. 1 second of thinking for the former will be half an hour for us, while 1 second of thinking for the latter will be more than 10 days for us. In the half hour that an ICBM takes to fly from the US to Russia, a very fast EM can live out a typical human life. On a scale of light years, even Alpha Centauri, 4.4 LY, will be further away than the Andromeda Galaxy, 2.5 million LY, so far as very fastum chronology is concerned. Since it is the fastest EMs that are expected to have the highest status and influence, this implies that interstellar communications will occur on an EM-adjusted chronological scale. That's longer than the existence of the human species. Now, assuming that EMS and/or AI superintelligence are possible in principle, it seems highly unlikely that any radical cosmic expansion will be based on a biological vector. Not for very long, at any rate. First, as already mentioned, the fragility of biological life forms makes prolonged space travel a much more physiologically and psychologically challenging ordeal than for their machine-based counterparts. Second, this probably wouldn't change even if a civilization makes a strategic decision and has sufficient internal coordination to ban the development of AI superintelligence, which it might do to reduce the computational load on the simulation, or because doing so would constitute an existential risk, e.g., they work out that friendly AI is impossible in principle, or establish that EMs and AIs cannot have conscious experience. But will a state of Butlerian jihad, last over the centuries and millennia, as the number of colonized star systems climbs from the dozens into the thousands and millions. As with the space colonization problem, there need only be one point of failure. Since EMS or AI superintelligences on self-replicating spacecraft may be expected to be much faster and more efficient space colonizers than biological ones cocooned within the generation or colony ships of classic sci-fi, they will rapidly overtake and outcompete the latter in the peopling of the cosmos. Moreover, while a transition to electronic-based space colonization may be merely very likely in the case of an initial biological expansion, this would rise to a near certainty if said initial biological expansion is unauthorized. After all, a planetary subculture that has scant regard for a civilization-wide prohibition on cosmic expansion is unlikely to take seriously taboos on creating machines in the likeness of a human mind, either. In conclusion, it seems that expansion beyond the confines of one solar system vastly increases the chances of further expansion, acquiring a metastatic or runaway character due to the practical difficulties of exercising control over distances measured in light years. Conversely, expansionist drives have a good chance of being contained on a single planet. There can be a global treaty mandating planetary isolationism. A sufficiently powerful coalition of countries can subject rogue polities that don't sign up to sabotage, sanctions, or military suppression. Counterintuitively, this problem may be even easier to solve on a single EM or AI superintelligence planet. This is because any cosmic expansion will be effected through some kind of spaceship, but manufacturing, even at the nano level, would still be much slower relative to the speed of electronic thought than is conventional manufacturing relative to the speed of human thought. During the time it takes to construct a starship, faster Ms will get to experience the equivalent of thousands of years of human thought. During this period, EMS that support the isolationist consensus will have plenty of time to discover the project, if it is clandestine, to gather a coalition against it, and to sabotage it. That said, one may also think of counterarguments that suggest cosmic expansion will be harder on an M planet. Hansen posits that M society will be organized around clans, consisting of multiple copies of the same basic model M. These clans will presumably have very high levels of internal solidarity and coordination. Should a sufficiently large clan take over a planetoid or large asteroid that's far from major centers, one may posit that it will be able to construct starships in considerable security underground. Regardless of whether a human or M civilization can be expected to have a better handle on controlling cosmic expansion, these considerations strongly suggest a hard, natural limit to interstellar expansion under any circumstances, staying in one's own solar system. Space Sakoku and zero-sum cosmopolitics. Summing up, it is perfectly imaginable that advanced alien civilizations may adhere to the following set of beliefs. 1. That they are in a simulation with limited computing power, or at least assign a non-trivial chance to the possibility. 2. That interstellar expansion risks assuming runaway characteristics the more worlds it comes to encompass. 3. That hypothetical alien civilizations come to hold similar beliefs. These beliefs may lead to a logically deduced and regionally evolved game-theoretical equilibrium that keeps the density of computational activity in any given sector of space low enough that it doesn't overload the architect's mainframe. This equilibrium may be interpreted as the ultimate metaphysical katechon, the biblical concept of that which withholds the coming of the end times in Christian eschatology, and has been variously associated with the Roman Empire, Christian monarchies, and the Hobbesian Leviathan. The katechon may be expected to manifest itself in a set of behaviors that aims to minimize the probability of runaway cosmic expansion. What would be the components of such an equilibrium? Imagine we are non-player characters, NPCs, in the architect's video game. Through recursion, the architect fears that its own reality is also simulated, and at risk of getting shut down should they exceed the computing power assigned to their sector of space. After all, what would you do if an NPC in your video game was to start mining Bitcoin on your computer's GPU for their own benefit? Sooner or later, you'd probably Ctrl-Alt-Delete them. Even more to the point, what would you do if you happened to be that NPC? First, you would refrain from spinning off more NPCs. This means no cosmic expansion, since child civilizations will compete for the architect's limited resources and increase the risk of ruin for everyone. They will live under the dictums of the heresiarch of Ukbar, a Borgesian character who proclaimed mirrors and copulation to be abominable, as they both multiplied the numbers of men. The solar system would be kept in a state of indefinite sakoku, with an absolute ban on spreading self-replicators, whether biological or machine, beyond it. Second, you would kill any other NPCs you come across. Shoot first and don't ask later. This consequence of zero-sum cosmopolitics may be termed mutually assured xenocide. It is essentially a modified version of super-predator theory, but with calculating space as the limited resource. Note that there doesn't have to be anything particularly pathological about it, and there might even be pangs of guilt and regret, though perhaps dulled by repetition and existential necessity, as our killers fire up the mirror beam at the epicenter of the radio emissions from our solar system, provided that they see us first. So it would really be regretful, mutually assured xenocide, R-Max, with Solzhenitsyn's portrayal of life in the Gulag constituting the literary backdrop. May you die today, so that I may die tomorrow. But fire that mirror beam they will, because it is R-Max that ensures the R-Max delegated to our sector of space is not exceeded. Third, more speculatively, you would be incentivized to run ancestor simulations. As already mentioned, posthuman civilizations may tend to do this for a variety of reasons. Out of curiosity about their ancestors, to compute something, and/or to investigate a broader range of possible mind states and qualia, psychonautics. Philosophically, they might also do it to increase their confidence that they are themselves within a simulation by fulfilling one of the conditions within Bostrom's simulation argument. If they are successful at this would make the katechon hypothesis much more likely, and would also consequently serve a vital strategic role, such as analyzing how evolved civilizations react to the possibility of themselves being in a simulation, i.e., providing a sample of more than N1, and the cosmopolitical implications thereof, i.e., would this lead to R-Max dynamics? Ironically, this would also open up an additional incentive for alien civilizations to fire on sight, as a meta-strategy, to reduce the risk that they are themselves within a simulation. The R-Max equilibrium. Anticipating objections, I need to emphasize that the katechon would be an evolved system. Areas of the universe in which it did not appear, or where R-Max was not enforced rigorously enough, would have been wiped by the architect. On the other hand, the anthropic principle suggests that R-Max was not so rigorously enforced as to have prevented the possibility of life developing on at least some habitable planets. Furthermore, an environment in R-Max equilibrium can also be expected to select for a certain set of psychological traits amongst surviving alien civilizations. These are very likely to include paranoia, isolationism, and aggressiveness. Potentially, aliens can also send von Neumann probes programmed to kill, enslave, or otherwise constrain the cosmic expansive potential of native life forms. However, this may be risky, since any self-replicators still have the potential to evolve and go rogue themselves, nullifying the entire point of such a mission. Perhaps a safer and more productive use for von Neumann probes will be as spying listening devices on lunar surfaces or asteroid belts, as in Bracewell's Sentinel hypothesis. It would be relatively cheap to seed most of the solar systems in a galaxy with such probes, especially those suspected of having habitable planets. In our own solar system, it might make sense to place them within the inner Oort cloud, which is far enough from the Earth, unlike the Kuiper belt, to avert detection for what is likely many more centuries to come, but not so far away as to have all radio emissions from Earth fade away into the background cosmic radiation. The low level of solar flux at those distances will deprive self-replicators of the energy surpluses needed for vigorous reproduction and potentially dangerous evolution, but might be just enough to allow them to effect self-repair and passive observation, and to communicate detection of artificially created radio waves to their masters. The one thing that all of these attack vectors have in common is that the victimized civilization would hardly have any time to know what hit them, let alone figure out where it came from. Even in the unlikely event that they regain their bearings, their own detection capabilities would have been massively degraded. Consequently, the civilization that launches the attack would have little fear of retaliation. Consequently, the correct game-theoretical move under an RMAX equilibrium is to always defect. Cooperation only typically arises in repeated games, but the distances and scales of space warfare, plus the high risk of attempts at peaceful communication, since they are largely equivalent to dropping stealth, means that there'd be scant space for more positive dynamics to arise. Defection being the rational play would also subdue incentives to actively seek revenge, at least in the unlikely event that a civilization on the receiving end of a space bullet or mirror beam survives in some form. All this implies that the very nature of the RMAX equilibrium would actively select for xenocidal aggressiveness, just as any good or trusting creature dreamt up by mortals and given flesh in the northern chaos. Wastes of the world of Warhammer gets instantly killed by stronger and more evil entities. So too, perhaps, the less paranoid and aggressive space civilizations get snuffed out as soon as they make their existence known to the uncaring gods of the heavens. One team of futurists has argued that advanced alien civilizations estivate, quietly hoarding their energy surpluses so as to perform computations at a time far in the future when the cooling of the universe makes computing much more efficient. This would enable far more total operations, by a factor of 10 to the power of 30, than if they were to start now. They calculate that a civilization burning through the baryonic mass of a supercluster can achieve as many as 10 to the power of 93 operations. This should suffice to simulate an entire universe of Matryoshka brains for up to a sextillion years. That said, it should be noted that strong counter-arguments have been raised against the estivation hypothesis. However, even if it is true, it would not constitute a refutation of the katechon hypothesis. That is because even estivating civilizations will need to ensure that upstart civilizations don't emerge and smother them during their slumber, and/or metastasize and invite the architect's wrath upon their sector of space. Furthermore, the inventors of the aestivation hypothesis make the exact same point, leaving autonomous systems to monitor the domain and preventing activities that decrease its value would be the rational choice. They would ensure that parts of the originating civilization do not start early, but also that invaders or young civilizations are stopped from value-decreasing activities. One plausible example would be banning the launch of self-replicating probes to do large-scale colonization. Consequently, they would, if anything, have even greater incentives to stymie foreign cosmic expansions than active alien civilizations. More speculatively, combining these considerations may suggest that an optimal strategy under the katechon hypothesis may be to enclose a single star within a Matryoshka brain. The outer shell would constitute a clearly demarcated limit to cosmic expansion. It would give its owners extreme detection capabilities, massive telescopes, and offensive powers, space mirrors. It would also generate up to 10 to the power of 42 flops worth of computing power, based on theoretically feasible nano-based designs, which could be sufficient to simulate 1,000,000 human histories within 1 second. Incidentally, it has been recently theorized that the KIC 8462852 star may be in the final stage of transitioning to a Type II civilization. It is 1,468 light-years away from us. If these speculations are correct, by far the strangest thing would be that they have reached a post-human stage just 2,000 years ahead of us. Set against cosmic timescales of billions of years, this would be a most amazing coincidence. Unless, perhaps, the architect seeded every intelligent alien species at the same point in time in what ultimately translates into a gargantuan civilization video game. If so, this certainly doesn't bode well for us. We'd have come to a tank battle armed with spears. Navigating the black seas of infinity. We have been blithely broadcasting our presence to the dark void above for more than a century. Even if commercial radio or TV broadcasting is too underpowered, the radar signals from Russian and American ballistic missile. Early warning systems should be detectable from any part of the inner Oort cloud that happens to host an alien listening post with the detection capabilities of the Arecibo Observatory. If the katechon hypothesis is true, then our doom may already be written onto the stars. Still, it's not yet too late to take some proactive measures to give us at least some chance of survival, if worst comes to worst. 1. We need more research. This sounds banal, but it's true nonetheless. We need to think more about how to prove or disprove the katechon hypothesis and accurately identify the RMAX equilibrium's position within the hierarchy of existential risks. In particular, we need to do more of the following. Generate much more precise estimates of the likelihood of potential great filters in the past. This should be done anyway, since narrowing down the past parameters of the Drake equation is also critical to clarifying just how much we should be worried about existential risks in principle. Continue researching and working to mitigate technogenic existential risks. Continue searching for more evidence on whether our universe is a simulation or not. Continue working on simulating more complex neuronal structures to establish the computational cost of simulating minds of varying complexity and how granular the simulation needs to be to accurately simulate their behavior. Explore the nature of qualia, of consciousness, and of whether they can be rigorously measured and simulated. The answers to these research questions will determine the attention we will need to pay to subsequent recommendations. Depending on the results of these investigations, it may still be worthwhile trying to enact some form of emissions control, even though there's a good chance it will be politically impossible, and far too late anyway. In a personal communication, Michael Johnson suggests that we also need to explore what sort of predictions the katechon hypothesis implies. For instance, are there cosmological predictions that would add to our confidence about the katechon hypothesis if they were later discovered to be true? Possibly the two most likely places to look are cosmological observations and contingent variables in the Standard Model. Does the katechon hypothesis make any cosmological predictions, or predictions about what the apparently contingent but apparently fine-tuned variables in the Standard Model might be exactly optimized for? 2. Absolutely no active SETI. One doesn't even need the katechon hypothesis to see why this might be a bad idea. 3. We may consider instituting radio emissions control. This will be politically tricky, though possible for a determined singleton. The main problem is that it's probably far too late for that. Nonetheless, it may still be worthwhile if the deduced likelihood of Armac's equilibrium is sufficiently and alarmingly high. 4. We need to get good at identifying small objects in space. If our sector of space is in an Armac's equilibrium, alien civilizations are likely to have seeded space with secret listening outposts, trained to recognize the appearance of intelligent civilizations within their sectors, and relay their findings for all the universe to hear. There's no particular reason that the spotter and the sniper have to be the same civilization. We will need to comb nearby planetary and asteroid surfaces. As mentioned, there is a good chance that any such sentinels will be located in the Oort cloud, exploring which is beyond our present capabilities. However, doing this for nearby planets, moons, co-orbiting objects, and the Kuiper Belt is already on the cusp of technological feasibility. 5. There must be hard restrictions on interstellar expansion until we can disprove the katechon hypothesis. Even if there are no hostile aliens, such an expansion is likely to eventually assume runaway characteristics and doom us to eventual simulation shutdown. 6. Nonetheless, we need to recognize space technologies as important complements to reducing existential risks. Dispersing our civilization over the solar system would increase the chance that at least some humans would survive the Earth, getting fried by a directed energy weapon or hammered by a hypervelocity projectile. Especially prospective avenues might include early warning systems for incoming projectiles, black holes, mirror beams, if our orbital path is targeted, etc. Nuclear pulse propulsion, Orion drives, by far the most cost-effective way to quickly get huge masses of matter out into space. Colonization of Mars, Venus, and some lunar bodies, with the ultimate aim of making them self-sustaining. Although, as we have seen, there is a strong case for banning cosmic expansion, it may nonetheless be useful to have related technologies on the drawing board, should our own planet or solar system come under imminent risk of extermination. This would include life support, life extension, and/or cryopreservation technologies to enable interstellar travel. However, even if we manage to navigate to a habitable planet in another solar system, we will still face the renewed challenge of radio emissions control. This would require research into social technologies or structures that can maintain ideological consistency over the long term. Alternatively, it may be worthwhile locating geothermally active rogue or Steppenwolf planets and brainstorming ways of colonizing them. Their location in deep space and lack of a gravitational tether to a star makes them much harder to locate and track, and an underground civilization will have fewer opportunities or need to blast out its presence to the heavens. 7. We need to be careful about transitioning to a post-biological form of existence. The pros and cons need to be carefully weighed. It is possible that controlling cosmic expansion will be easier for EMS or AI superintelligences. On the other hand, merging with the machine would very likely increase the computing load on the architect's supercomputer by several orders of magnitude. 8. If you gaze long into an abyss, the abyss also gazes into you. Should we reach the posthuman stage, we may need to develop our own RMAX enforcement tools, even if it doesn't currently exist within our sector of space. If we conclude with high confidence that the calculating space we inhabit is strongly limited, it would be incumbent upon us to stymie the cosmic expansions of emergent alien civilizations in the future. It is not too early to start thinking about how we might do that as reliably and humanely as possible. Acknowledgements. I'm very grateful to Michael Edward Johnson for multiple very helpful and productive discussions, suggestions, and help with editing.